All right, the third and final FRQ of the day. This time is 2015, question one. Again, staying on theme with a calculator problem. Um, we have the whole thing kind of shown here for you with the answer key included. We're going to talk it through on the whiteboard and see what we can do. So here we go. The rate at which rainwater flows into a drain pipe is modeled by the function r, where r of t equals 20 sine of t squared over 35 cubic feet per hour. Okay, so we're going to stop there and note that this is a rate function from 0 to 8, right? So R of t is a rate, right? It's the rate at which rainwater is flowing into a drain pipe. The pipe is partially blocked, allowing water to drain out the other end of the pipe at a rate modeled by d of t equals, and you can see that function, cubic feet per hour. Here again, very similar to the first problem we tried today where we have two opposing rates. We have rainwater flowing into the drain pipe at a rate of r of t. So I'm going to note that over here. I'm going to write in r of t, and we got water flowing out of the drain pipe, d of t, and these are both in cubic feet per hour. Units are important, especially if they ask for them specifically. All right, there's our initial condition, classic, right? At time equals 0, we have 30 cubic feet of rainwater in the pipe. Gonna need that eventually, just to have the feeling. A, how many cubic feet of rainwater flow into the drain pipe during the 8-hour time interval 0 to 8? You can see it there. I'm literally on my answer sheet going to write the integral from 0 to 8 of r of t, because it's the rate at which that water's flowing in, dt. I'm going to put that into my calculator, and I'm going to get 76.570. And that's all that I would need to write for A. Literally, they know what r of t is, so you can just write it as r of t. They know, you know, I know, it's good, right? Do that in your calculator. Double check your answers. Double check that your parentheses are correct. 76.570 cubic feet, right, of water flow into that drain pipe during the time from 0 to 8. Notice it's not asking how many feet are in there, right? Just how many are flowing in. They often will start problems out like this. They did in the first question we saw today, right, from 2017. Very similar start. All right, let's scroll up here, give ourselves some room, and talk about B. B, is the amount of water in the pipe increasing or decreasing at time equals 3 hours? Give a reason for your answer. Man, this really seems familiar. Let's compare R of 3 minus D of 3, right? It's the rate in, that's supposed to be an N, minus the rate out. What's happening here? Well, if you compare those two, that difference is, regardless of what it actually is, right? That difference is negative. It's a negative difference, which means, right, that R of 3 is less than D of 3. In other words, D of 3, the rate at which water is flowing out, is greater than R of 3, the rate at which the water is flowing in. Therefore, to answer the question, is the amount of water in the pipe increasing or decreasing? We're decreasing, right? We're decreasing because R of 3 is less than D of 3. It's that easy. Right now, you wouldn't necessarily even have to write it out like this. They do on the answer sheet. You could literally just find the value of R of 3, the value of D of 3, and compare them one to the other, right? As long as you consider those two values and then talk about this as your reasoning, you're going to get both points for letter B. Let's move to C. At what time, t, on the interval 0 to 8, is the amount of water in the pipe at a minimum? Justify your answer. Okay, at a minimum. So take a deep breath. How do I find a minimum? Well, I take the derivative, right? I set it equal to 0. I find my critical points and I test. So I know that the amount functions, right, are really the antiderivative of R and D, which means R and D are kind of like the derivatives here, right, of the amount of water in the pipe. R and D, really specifically, R of t minus D of t, that itself is kind of quote unquote the derivative of the function that gave us the amount of water, right? You can see in the answer sheet, right in letter C, that 30 plus the integral from 0 to t, that is your amount of water. So if you take the derivative of that, R of t minus D of t, you can consider, when does this equal 0? By taking the derivative, setting equal to 0, finding your critical points, and testing, you can figure out what the minimum is here. Now, let's think about this more specifically. What times might this occur? Well, to find when this is equal to 0, I'm not going to use like my home screen to solve this thing. I'm probably going to put R of t minus d of t into my graph screen and see on the interval 0 to 8 when this is equal to 0. I'm going to use my zeros function in my calculator on the graph screen to see, okay, when is this thing equal to 0? I'm going to put it all in. It's going to take a second. I'm going to make sure I get it right. It's all good. So I see that this is equal to 0 specifically at time equals 3.271658. Right? That's the time when R of t minus d of t equals 0. The derivative equals 0. But that's not my only potential time where there could be a minimum here, because I'm looking for the absolute minimum on an interval. What I really need to do is I'm going to need to compare that time, or the amount of water at that time, to the amount of water at my endpoints. Because that's my only interior critical point, I really have this situation where I have t equals 0, t equals 3.27 and change, and time equals 8. Those are my three candidates here. And as you can see, you can then figure out exactly how much water is in the pipe at each of those times. How do you do that? Well, 30 plus the integral from 0 to t of r of t, or r of x dx, you could write it that way so the variables agree, right? Minus the integral from 0 to time t of d of x dx. They wrote it as one integral. I wrote it as two separate integrals. It's the same thing. So this is, as usual, the initial plus how much water was added minus how much was removed, right, or drained. So we have our initial plus how much was added minus how much was removed. And I can evaluate this integral, these two integrals, at this time, and then I can step back and rewind, and then I can evaluate them at this time. And I can see exactly how much water was in the pipe at those three different times. It's really important that I know that I need, or in the final answer, I don't need the amount. The question is saying, at what time is the amount of water in the pipe a minimum? Justify your answer. My justification is that the amount is a minimum. I'm going to set up a table in my work just like they did in their answer sheet. But my final answer has to be that the time equals 3.272. That's when there's a minimum. Why? Because the amount at the endpoints, when compared to the one critical point, the one interior critical point, the one interior critical point yielded the minimum amount of water on the interval. Let's go to D. Right, and we've seen that before in C. Whenever we have an absolute min or max on an interval, we want to compare our critical points to our endpoints, and we can set up that table just like they did to solve. It just becomes a little complicated because of the complicated functions, but we have a calculator and we have time to do it. So take your time and make sure you're specific with everything. D, the pipe can hold 50 cubic feet of water before overflowing. For time is greater than 0, water continues to flow in and out of the pipe at the given rates until the pipe begins to overflow. Write but do not solve an equation involving one or more integrals that gives the time w when the pipe will begin to overflow. Okay, so I already know the amount, right? I already know the amount of the function for the amount of water. It was 30 plus the integral. And they rewrote this because they say the time is greater than 8, right? But don't solve an equation involving, right? An equation involving one or more integrals that gives the time w. We need to make this w up here, that integral from 0 to w. Because what we're going to do is we're going to say initial plus the total amount added and removed equals 50. And if we can find the time when this left side equals 50, then we're good to go. So our initial plus the amount, how much does this move? Well, it gets added at a rate here, right? It flows in minus flowing out. Oh, let's zoom it over here. here, right? So I'm going to write this as one integral. Oh, give me that eraser. I'm going to write this as one integral. Put my brackets in here to be kind of official about this. Kind of got sloppy. And we'll put that equal to 50. Let's talk about what this means. What I'm saying is that the initial amount plus the amount that flowed in minus the amount that flowed out equals 50 at some time. There's some value of W that I can put in, and I got to use W because they're telling me to use W. There's some value of W that's going to make this amount equal to 50. Think about what we did in the last part, in part C. At time equals 0, we had 30 cubic feet of water. When we put our time into this same function here, it gave us our amount. Right? It gave us the amount of water at any particular time. I'm just going to take that function and say, okay, let's make this time the variable and set this thing equal to 50. If you can give me the time when this thing is going to happen, right? When this 30 plus the integral is equal to 50, that would solve it for me. So it's 1 point for the integral, right? The integral from 0 to w of r of t minus d of t dt, and 1 point for the overall equation. So that involves the initial condition 30 and setting it equal to 50 overall. So the kicker is kind of being able to set that up from the beginning, right? That initial plus the integral that represents the change in time. And if you go back to the first problem we tried today, this is a constant theme in these sort of opposing rate type of problems, right? Where they want to know a function somehow, some way, or an amount of whatever it is, given that there's two functions, one adding something and one subtracting something. So you have to set up that integral. Hopefully these make sense to you after going through them. We'll try some more here down the road. For now, feel free to jump into any missing work, whether that's some of the online virtual work or any corrections that you have to figure out. I hope you have a wonderful day and a great break, and I hope to see everybody soon. Take care.